Hello, my name is Ariail and my partner is Ben Faulkner. This is our A1601 glider report. For this project, we designed, built, and flew a balsa wood glider. The goal of this project was to use the things learned over the semester to design a glider that can reach a minimum of 20 feet. A few requirements for this design process. The size. The vehicle must fit in a 16 by 16 inch box from the top view. Durability. The vehicle must remain intact during flight. Components. The vehicle must not contain any electronics. Flight distance. The vehicle must fly at least 20 feet. Propulsion. The vehicle must not contain any propulsive elements. Throwing. The vehicle must be hand thrown. Some measures of success for these. The glider fits in the box. The glider stays successfully intact. The vehicle does not contain any electronics. How far the glider flies. The vehicle does not contain any propulsive elements. And the vehicle is hand thrown. Some alternative designs that we considered. Elliptical wings offer lower drag, rectangular wings offering higher lift area for wing shape, wing placement, top versus bottom of the fuselage, stability versus control, respectively. Lateral placement of the wings offered how the glider flew, and this was determined through iterative mass testing. And the tail configuration, T-tail versus V-tail, offering drag reduction and stability, and depending on ease of manufacturing. The elliptical wings offer lower drag, which is better for glide distance. Lower drag means the initial velocity carries the glider for longer, allowing the glider to maintain a higher airspeed for longer. The wing placement. The top of the fuselage was decided since stability allows for a more stable, steady glider flight. Lateral placement a few inches from the nose, with mass on the nose. And the tail configuration, we decided to make a T-tail since it was easier to manufacture and we could ensure that we were placing the fins at correct angles and not skewed angles. The sizing process and initial design choices. We decided to use as much of the space that we were given to maximize the total lift area of the glider. The wingspan of the glider was between 14 and 15 inches, around 14.7. Fuselage was 12 inches, and the fins were each 2 inches tall. Our initial set of design choices were to maximize lift area and reduce drag with elliptical wings, ensure stability with the T-tail and top of the fuselage wing placement, and balance the CG and CP through iterative weight testing.
Testing and iterations. Testing stability. Stable after adding a mass component to the nose, but still tends to go up and stall. Iterations, areas to improve. Mass performance. It kept falling off, which caused the nose to go up and stall. Testing performance. Foam glider barely reached 20 feet. It lost airspeed quickly due to significant drag, presumably from the thick foam. Iteration design changes. Changes to the shape of the mass to fit the fuselage better and add a slight negative angle to the tail fins. Test glider on the left and finish glider on the right. The final design incorporated a slight negative tail tilt that added stability, a top mounted elliptical wing that reduced drag, and a mass fitted component to the nose that stabilized and absorbed impact. The centre of gravity of the balsa glider was right under the middle of the wing, roughly half an inch from chord over 4 since the chord is 2 inches. These designs met all design requirements. It was within the size limitations, hand thrown, did not contain any propulsion or electronic elements, stayed intact, and reached over 20 feet. Ours personally reached 33. Conclusion. This project provided us with the opportunity to explore alternative designs and evaluate them with the design process. It allowed us to start from scratch and come up with a creative solution to the specific problem our design was facing, rather than all starting from the same kit like in the rocket project. Our design could be furthermore improved upon by maximizing the lift area by making the wingspan the hypotenuse of a 16 by 16 inch square. We could also test different horizontal tail stabilizer angles to determine which provided the best flight path.